Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last lecture, we have discussed about a very important attribute of transition metal organometallic compounds, particularly with respect to their reactivity, as to why these compounds are so reactive, so difficult to handle, why they decompose and what are the reasons behind that. And while analyzing, we came upon the main factor responsible for extremely high reactivity of these transition metal organometallic compounds, and that is called beta elimination reactions. In the course of discussing beta elimination reactions in details, in the last lecture, we aimed at understanding how this reaction was occurring, how this reaction mechanistically was proceeding, and what was established was through experiment was the fact that these reactions proceed if there is a hydrogen at the beta carbon of the alkyl group, which is attacked by the transition metal, leading to the elimination, hence the name beta elimination, resulting in a metal hydride and an olefin. And this was established by a classical isotope modeling experiment in which a beta hydrogen was replaced with a deuterium, resulting in the formation of a metal deuteride, which sort of established the fact that a beta elimination proceeds by elimination of the hydrogen placed at the beta position of the metal alkyl bond. In the previous lecture, we further discussed about the various strategies that are often employed in suppressing beta elimination reactions. These can be done by the following two strategies, which we had discussed in the last lecture. First one was formation of olefin be made sterically or energetically unfavorable. And this was made possible by application of this Brett's rule, whereby formation of olefin at a bridge carbon becomes unfavorable. And the example of this are norbornene ligand, which does not undergo beta elimination, even though there is a beta hydrogen in the ligand at its beta carbon atom. We had a fairly detailed analysis of this particular rule, and we found that this can be favorably used for stabilizing several high valent oxidation states of metal, for example, iron 4, chromium 4 complexes and several others, which otherwise would be difficult to stabilize. Now, in the previous lecture, we also discussed about a string of ligands which does not have beta hydrogen at the beta position and does not form beta elimination reaction. So, designing ligands without beta hydrogen would also suppress beta elimination reaction. The second strategy involved designing ligands without beta hydrogen, as these ligands, in absence of its beta hydrogen, is unable to undergo beta elimination reaction. Now, with this in background, we come to another interesting strategy for today's topic, that is, if the coordination of the central metal atom be made saturated, so the beta elimination can be stopped. So, this strategy is about inhibiting beta elimination by coordinatively saturating the central metal atom. In this, it takes into fact that beta elimination proceeds via transition state in which the central metal atom attacks the sigma bond of the carbon hydrogen bond placed at the beta position of the ligand, and thereby the metal undergoes an increase in coordination number. So, the implementation of the strategy requires such that the metal be coordinatively saturated. So, the metal, despite having a vacant d orbital to attack the CH sigma bond of the beta position, it is unable to do so because of coordinative or steric saturation. For example, let us analyze this third strategy where the metal atom is coordinatively unsaturated. For example, let us look at thermal stability. Now, thermal stability of these two compounds, let us say titanium tetramethyl and titanium tetra CH2 C CH3 whole 4. Now, both of these does not have beta hydrogen. This only has alpha hydrogen, and this at beta carbon does not have a beta hydrogen. This is a neopentyl group. And as both of these ligands do not have beta hydrogen, so one would think that they may be equally stable, but actually that is not the case, as titanium tetramethyl shows a decomposition temperature of minus 40 degrees centigrade, whereas titanium tetraneopentyl compound gives a melting point of plus 90 degrees centigrade. So, what can see that there is huge difference in stability between titanium tetramethyl and titanium tetraneopentyl, despite the fact that both titanium tetramethyl and titanium tetraneopentyl does not have beta hydrogen. So, obviously, there has to be some other effect responsible for extra stability of this titanium tetraneopentyl complex, and that extra stability comes from this coordinatively saturation environment around titanium. So, titanium being flanked by all these bulky neopentyl group, 4 of them is very much coordinatively saturated, and hence it does not decompose. So, this is in tune with the strategy of the third one that we are discussing, that coordinative saturation at the metal center. For example, again let us take a look at another set of complexes. For example, if we look at thermal stability of the following two compounds. In this case, zirconium tetramethyl, similar to titanium tetramethyl we had discussed earlier, and zirconium tetrabenzyl, both does not have beta hydrogens. So, this does not have a beta hydrogen and this also does not have a beta hydrogen. So, this is a benzyl ligand, no beta hydrogens. So, in this case what we see, decomposition temperature in this case is minus 15 degree centigrade, whereas zirconium tetrabenzyl, the melting point is 132 degree centigrade. So, there is a tremendous increase in stability despite the fact that both of this compound does not have beta hydrogen and there is a significant increase in stability on the tetrabenzyl, and this is also explained by the fact which we are discussing as a part of the third strategy, that the central metal atom is coordinatively saturated. So, what we are seeing right now is the manifestation of this third strategy of how coordinatively saturated metal center may increase or impart extra stability to transition metal complexes in addition over and above of what comes from the ligand which it does not have a beta hydrogen. So, let us sort of understand the fact that how come coordinatively saturated central atom leads to extra stability. To understand this, we need to understand or take a look at the instability of compounds like zirconium tetramethyl. So, for stability, thermal stability, of coordinatively saturated metal center. As mentioned, to understand this, we need to take at the following two compounds. For example, titanium tetramethyl, which does not have a beta hydrogen, decomposes at minus 40 degree centigrade, whereas the corresponding lead tetramethyl, which is a main group sigma alkyl metal complex that also does not have a beta hydrogen, only has alpha hydrogen, distills at 110 degree centigrade in 1 bar pressure. So, this shows that this main group lead tetramethyl is exceptionally stable that one can distill it. So, what is the reason why this titanium tetramethyl is so reactive that it decomposes at minus 40 degree centigrade? And the reason comes from the fact that decomposition arises via a bimolecular pathway. What is this bimolecular pathway resulting in the decomposition? To understand this, that titanium tetramethyl is coordinatively unsaturated. This unsaturation comes from small size of the methyl group. As a result, titanium being early transition metal and extremely electron deficient, can undergo this bimolecular pathway by attacking the titanium methyl bond of the neighboring molecule. As a result, this titanium methyl bond becomes weak, as they convert from classical 2-center 2-electron bond to a non-classical 3-centered 2-electron bonds, leading to their decomposition. So, what is very interesting is that for electron deficient element like titanium, if it remains coordinatively unsaturated, then it can interact with the titanium methyl bond of a neighboring titanium tetramethyl compound, thereby weakening it and resulting in decomposition of the compound. Whereas, in lead electron rich main group element, such bimolecular decomposition pathway is not possible. For tetramethyl lead, bimolecular pathway not favorable because of higher energy MTD orbital. For undergoing such decomposition pathway. Whereas, titanium tetramethyl, which is coordinatively unsaturated, and decomposes at minus 40 degree centigrade, can be made more stable if it is made coordinatively saturated, and that can be done by adding a bipyridine ligand, for example plus bipyridine, to give this compound which now has become coordinatively saturated, due to chelation. So, what is observed that by addition of this bipyridine ligand, which is a chelating ligand, the coordinative saturation of the titanium center is increased in this titanium tetramethyl complex, and hence this become very stable. So, what is emerging out of this third strategy is that the third strategy is a very potent approach for increasing stability of transition metal sigma alkyl complexes, and that can be achieved by increasing the coordinatively saturation of the central metal atom. Here is another example of coordinatively saturated central metal atom in this tungsten hexamethyl complex. This is very stable relatively and has a melting point of 30 degree centigrade. Now, this is one of the homoelectric rare complexes where the metal methyl homoelectric complex is so stable that its melting point is around 30 degree centigrade. This can be prepared from the reaction of tungsten hexachloride with methyl lithium, giving to tungsten hexamethyl. This complex is electronically as well as coordinatively saturated. And also it does not have a beta hydrogen, and hence it is stable up to plus 30 degree centigrade, and in contrast the titanium tetramethyl has a decomposition temperature of minus 40 degree centigrade. These tungsten hexamethyl being both electronically and coordinatively saturated becomes significantly more stable than the corresponding titanium tetramethyl, and also this exhibits a unique kind of coordination geometry. For example, the most common coordination geometry for a metal complex having a coordination number 6 is octahedral, whereas tungsten hexamethyl shows trigonal prismatic geometry. Which is very different, and the structure of it can be shown over here. So, this is kind of can be seen as a prism whereby the 3 vertices occupied by 3 chlorine atom, the top one and the bottom one, and tungsten sits in the middle. Now, in this there are several other complexes which shows similar trigonal prismatic geometries, and these are mainly metal D0 centers like zirconium hexamethyl, niobium hexamethyl, tantalum hexamethyl, molybdenum hexamethyl, and D1 complex like rhenium hexamethyl. So, this trigonal prismatic is a very unique geometry which is explained by quantum mechanical calculations, and even VSRP fails to explain the reason for this. So, with this, let me summarize today's lecture. The main point that we have been dwelling upon today is that how coordinatively saturated central metal atom may affect beta elimination, and we saw that transition metal which is coordinatively saturated does not undergo beta elimination reactions that easily, resulting in suppression of beta elimination pathway and enhancing the stability of transition metal organometallic compound. And with this, we are going to still study in bit more detail that what happens when all of these strategies that we have been discussing put together in the same example, how the stability of these compounds may be enhanced. We are going to discuss all of this and many more in the next lecture, and I hope that you found this today's lecture very interesting one. With that, I look forward to being with you in the next lecture. Thank you.